Today's video is part one on a multi-part videos that have to do with nuclear chemistry. Today we're going to really drill down on radiochemistry. We hope you can understand how nuclear chemistry differs from the types of non-nuclear chemistry you've learned so far. I'd like for you to understand in nuclear chemistry there's something called radioactive decay, and I'd like you to know the particles that are emitted, how to balance the equations associated with that. I would like for you to know by looking at the isotope whether it is radioactive or not. Compare three types of naturally occurring radiation and understand their, qualitatively the health effects, and also to know some good uses of radioactivity. So the big picture, just to get started, is nuclear reactions. There might be three general types of reaction, and as a reference I'm going to put down a common non-nuclear reaction, which is just the combustion of coal, add oxygen, make carbon dioxide. Energy is just on the range of 90 joules for every gram of coal you burn. So one of the first types of nuclear reactions is called radioactivity, and that's where you have an atom that is actually emitting something out of its nucleus. Part of its nucleus is falling apart. The energy emitted is about 140 joules per gram, so very comparable to non-nuclear chemistry. Fission is a little different. This is where you basically have a stable atom that gets collided with an outside particle, and it makes it fall apart into two smaller atoms, and then also emit some more parts. And one of the keys here, besides kind of understanding conceptually that an atom is split in half into two smaller atoms or multiple smaller atoms, is the order of magnitude of the energy is about 1 billion times. And then finally we have fusion, which is where two small atoms collide and make a larger atom, and this is about 4 times larger in energy than fission. So focusing on that first reaction, radioactivity, is what we'll talk about the rest of this particular video. I would like you to compare chemical reactions to radioactivity. In chemical reactions, atoms recombine to form molecules. The atoms themselves remain intact. The interactions occur in the atomic shell via atoms. In other words, it's the electron manifold that's involved in these reactions. We know it's under equilibrium control. Can reverse it or control it according to Le Chatelier's principles. And then finally, when it comes to the rate, we know that it's temperature dependent. It depends on a slow step of the mechanism. You can alter that with temperature and things like complexity and catalysts. Let's compare that to radioactive decay. In nuclear reactions, new atoms are formed, but the mass is no longer conserved. In other words, I start with uranium, but I might end up with thorium and a particle that flies out of the nucleus. This occurs out of the nucleus, not out of the electron shells. The shells are rarely involved. So you have uranium, it loses something out of its shell and becomes a new element. Particle flies out, it's a little bit of a distance, and so the implications of that are that it's not under equilibrium control, it's not really reversible. So Le Chatelier's principles don't apply. In terms of the kinetics, it's usually first order, but it is not influenced by temperature, catalyst, or complexity. So one of the terms that's associated, obviously, is the nucleus, which is made up of protons and neutrons. Collectively, we might call those the nucleons. They're measured with the mass number, which generally you would just say the mass number is the total number of protons plus neutrons. And then altogether, you might call that particles or pieces of the nucleus the nuclides. When you look at a nuclear symbol, the bottom usually represents the number of protons. I'll show you a little variation on this here in a minute. The top number identifies the mass number. That mass number is usually associated with the common name, so this is particular is uranium-238. If you wanted to find the number of neutrons, you would subtract the atomic number from the mass number, give you the number of neutrons. In this case, 238 minus 92 is 146 neutrons. You'll hear the term isotopes quite often, and that basically is where you have the same number of protons but different number of neutrons. So with that in mind, I'd like you to kind of practice your General Chemistry 1 skills. Can you take this symbol of thorium-234, figure out its name, protons and neutrons? Can you take the name and then turn up the symbol, the protons and neutrons? So why don't you stop the video, take a minute, see if you can fill out this table, remind yourself of how you do that. This is great practice going into nuclear chemistry. So how did you do? Thorium-234 is based on the mass number. It has 90 protons. You subtract to find the number of neutrons. If it's phosphorus-30, then the 30 goes on top. Phosphorus is kind of almost redundant with the number of protons. You can't separate those two. Okay, another way to think about this notation is that you might want to consider this bottom to be the charge of the element. So that will work. It will also count protons, because for every proton you're going to have a positive 1 charge. But if you, for example, had an electron which has no protons, you might just mark the bottom with the charge, and then the top has nothing in the nucleus. So here's a proton with a +1 charge. Something in the nucleus. Obviously here's a neutron, no protons, no charge, and then you have 1 item in the nucleus, or a total count of protons and neutrons on top. I'm just showing you that sometimes if the particle is emitted from the nucleus, even though it is an electron, we might call it something different. In nuclear chemistry, call that a beta particle. And we might sometimes mark it with the symbol of the electron, or we might mark it with the Greek symbol beta. This is a positron. It's the anti-electron. No protons or neutrons involved. Net charge is positive. When a positron hits a beta particle, they basically turn into pure energy, and matter disappears. So here's uranium-238, standard notation. Still works that you can think of this as either 92 protons or 92 positive charges. Here's an alpha particle which has 2 protons, 2 neutrons, total count of 4. Again, just showing you that you might realize that this is the same thing as helium-4. It just flew out of the nucleus, so you might either see it marked as a helium nuclide, or you might see it marked as an alpha particle. They're the same thing. So many nuclides are unstable and they spontaneously emit radiation, process termed radioactive decay. It usually results in the creation of a new nuclide and the emission of a radioactive particle, pure energy, or both. Quite often we might refer to that new nuclide as an isotope. The driving force is finally to arrive at a stable isotope that no longer emits radiation. The decay scheme is just the various steps. So just one little reminder, and I'll show you one here in a minute, that things don't always just have one type of emission. Sometimes they'll emit, the product will then emit, that product will then emit, until finally the product is stable. Now there are 5 types of radioactive decay. You need to learn the names. The name is usually associated with the particle emitted. Now the keys to learning radioactive decay schemes. Know your 5 types of decays. We're going to talk about that next. Understand the essentials of a balanced equation. And the essentials are basically that the charges along the bottom in the reactant side always equal the sum of the daughter nuclide that's formed and the particle that is emitted. These sum up. So you can see, for example, that when radium decays into radon and an alpha particle, the protons sum up on the product side to the reactant side, and the mass numbers on the product side sum up to the mass numbers on the reactant side. And that's the key to balancing one of these equations. The last thing is I'd like for you to know how to identify stable isotopes and the type of decay needed to get to that stable isotope. So here's your 5 types of decay. An alpha particle, in essence, is 2 protons and 2 neutrons emitted from the nucleus. Beta particle is a little more complicated. It looks odd that you basically would grow protons, but the idea is that one of the neutrons that was previously counted as one of these 63 particles in the nucleus decomposes into an electron which popped out, so we call it a beta particle, and it leaves a proton behind. So in leaving a proton behind, the bottom number goes up, but that original neutron that was counted in this 63 is now the proton that is still counted in this 63, so the number doesn't change. Gamma is basically you start with a particle that has a lot of energy, unspent energy. It releases the energy, but it does not change any forms. It releases no particles. This is not an event that happens by itself. It usually happens as a result of recoil velocity from being emitted. So think about this radon right here, or this copper isotope right here. It has energy because it just threw a particle out. So originally here's the nickel, throws a particle, makes this new, what we call the daughter nuclide, and that daughter now has all this extra velocity from throwing something. So this is according to Newton's laws, the third law, that for every action there's an equal and opposite reaction. So the way it decays that energy is through a gamma decay. So this is exemplified right here. Positron is where you basically consider a proton turning into a neutron and emitting the positron particle. So again, proton leaving, so the count goes down, but the fact that the proton turns into a neutron, that keeps this total count the same. And then the positron's emitted. And then electron capture happens on the reactant side. The way to think about it is a proton reaches out and grabs an inner shell electron. That makes this proton into a neutron, so the count doesn't change because I lost a proton, became a neutron, so the count doesn't change. But the fact that I lost a proton changes the bottom number. Again, I'm just reminding you that, sometimes these Greek symbols are changed to the element they might represent. Beta into the electron, the alpha into the helium atom. Don't let that throw you off. So let's talk about how we could predict whether something's going to undergo radioactive decay or not. And one of the keys is to kind of start by finding your number of neutrons, divide it by the number of protons, and that will give you a number that you're going to use to find your line of stability. So now, right here, there's a reference line that's written in this chart that's a 1-to-1. For every proton, there's a neutron. That's the 1-to-1 line. All right? And that's helpful because what you see right away is that way up until about 20 protons, the stable elements are in a 1-to-1 ratio. All right? So that's one way to know if it's one proton for every neutron anywhere below element number 20, which is about calcium, then you're going to know that it's basically stable. If it's above that, there's going to be a certain decay, and if it's below it, it's a certain decay. Anyway, this is the line of stability. This is what things are trying to move towards, where they no longer undergo radioactive decay. So as we move away from the line of stability, once we break that, number 20 there, the most it gets to when you divide is 1.5. So anything that's greater than 1.5, if you're dividing, get 1.6, 1.7, you're going to assume that it's above the line of stability. If you divide and get below 1 down here, or below 1.3, 1.2 in here, then you're going to know, oh, wait a second, that's below the line of stability. Get above this number right here, 83. That's a magic number of bismuth. It's assumed that everything above that does alpha decay, so that's simple enough. If you're above the line of stability, things undergo beta decay. If you're below the line of stability, you will undergo either beta emission or electron capture, and you are not going to be held responsible for knowing which of these two. You'll just know one or the other. Now this is kind of an interesting little fact that when you're down low, usually it's 1-to-1. And here's a great example. The stable isotopes of helium with 2 protons, 2 neutrons, 100% of the isotopes you would find would be stable and they're that form. Okay, but I'm just kind of showing you these are all even. So even protons, even neutrons, that's generally how they occur, but there's always a little bit of an exception. Here's beryllium. The stable form of that is slightly off. It's an even number of protons and an odd number of neutrons. And it's interesting when you look at things that are odd. In other words, 9 protons, in order to be 1-to-1, you'd have to have 9 neutrons. Both of those are odd. That's very uncommon. So here's another example where the one that's most common when you have an odd number of protons is the one that's odd protons with 1 extra neutron. So it's very, in the general term of things, and you'll see this in different books, it'll say that when you're down in these low numbers, it's usually 1-to-1, but it's very uncommon to have both an odd number of protons and an odd number of neutrons. But of course, there's always exceptions. A classic one is nitrogen. 7 protons, 7 neutrons is the common stable isotope. But for memorization purposes and just kind of having a rule of thumb to work off of, I would generally say if you're below 20 protons, it's going to be stable if it's 1 proton to have 1 neutron. And if it's an odd situation, I would just add 1 neutron, and that's where it's stable. All right, so here's a decay scheme just so you can understand. If you start way up at uranium 238, which has 92 protons, it's going to start decaying until it finally gets down below 83, until it finally gets to the line of stability. And when you're up high, above 83, it predominantly undergoes alpha decay. And here's 1, 2, 3, 4, 5, 6 steps of alpha decay, and now you're getting below 83. You're at lead 82. And within that, there were a couple beta decays, but just generally speaking, and that's the part we're trying to teach you, generally speaking, when you're above 83 protons, it's going to undergo alpha decay. So, with those principles in mind, let's do a little practice. Let's look at these isotopes and figure out what decay they'd go through. We're going to start with this first one. The first step is always subtract so you can find the neutrons and divide by the protons to figure out the neutron divided by proton ratio. In this case, 12 protons, 12 neutrons, it's 1. It's even and it's less than argon, so therefore it is stable, no reaction. All right, here we do the exact same calculation. 28 minus 12 gives me the number 16 divided by 12. It's 1.33. In this area, we know we're very close to the 1 line if you're stable, so you're above it. So that would be beta decay. And then you just basically remember your rules for mass numbers should add up. Atomic numbers should add up from the reactants and products side. 13 minus 1 is 12. 28 plus 0 is 28, and then you can just fill in the blanks. What is the element, or the isotope in this case? All right, we get down to here. There's a number above 83, always alpha decay. There you go. Use your rules and fill in. This last one, now we've got 55 by 53, that's about 1. Very close to 1, but the number's fairly high. You're well above that 20. So we know we're lifting above 1. So this number must be below. And remember, in this case, it's one of 2 mechanisms, and you don't have to know which one. You just need to know how both would look. In the first case, you could do electron capture. That would give you the product of iodine 108. In the second case, you could do positron emission. That'll also give you the product of 108, iodine 108. So here's a chance for you to practice. So why don't you stop the video, try and complete the reaction scheme, restart the video when you're ready to check your work. So let's see how you did. In the first one, when you do this, it's below the line of stability, below the 1 line, so you know it's going to be either electron capture, beta decay. The second one, you're above 83, so you know it's alpha decay. In the third one, because it's 1 to 1 and it is below 20, you know it's no reaction. Here you basically do a division. You see it's 1.37. It's fairly early, so it's picking up above the stability line, so that must undergo beta decay. And basically, this is a chart that shows you that you're exposed to a lot of radioactivity. It happens very naturally. Even things like just flying on a plane, it gives you exposure to a certain amount of radiation from the sun. If you live in a brick house, a lot of those materials have radioactive materials as part of them. It's nothing that mankind has done. It's just naturally occurring. And then there are things that we do in medicine, etc., like X-rays that do expose you to radiation. But generally speaking, the average person in the United States is exposed to about 650 millirems annually. And a rem is a measure that explains how this radioactivity would affect human tissue. How dangerous is that? So to put it in perspective, if you're anywhere from 20 through 100 rems, you would have decreased white blood cell count, possible increase in cancer risk. 100 to 400, you start to get radiation sickness. Once you get to 500, you have death. And just to put that in perspective, that is in rems down here. You just, from background radiation, you would have basically 0.650 rems on an annual basis. It's total natural exposure. None of that's even close. You're orders of magnitude above the first place where you might start to have health effects. I'd like you to understand qualitative health effects from 3 natural types of radioactive emission. The first one is the alpha particle. It's identical to the helium-4 nuclei. It's emitted from a proton. You know it's a very large, massive particle. It's the largest of the ones you study. And the way to think about it in terms of health effects, it has the least amount of penetration. You can block it with just your skin, or a piece of paper would even block an alpha particle. But the problem is that whatever is directly close to it, in other words, if you ingest it or you get it inside your body where there's live active cells and it gets close to those cells, it can actually do massive damage because it is the most ionizing. It is a +2 charge flying through space. Now, on the other hand, you have beta particles, which are equivalent to electrons, so they're ionizing indeed, but you can be exposed to electrons by just anytime you get around electrostatic shock, but they are very high speed. Again, they're medium penetration. You can stop them usually with a smaller, a lab coat or a smaller cloth that would block a beta particle, and they're a little less ionizing. And then finally there's the gamma ray, which is the most penetrating, but because it has no ionizing ability, it's the least dangerous. But you would have to have inches of lead to literally block a gamma ray from traveling through material. So in terms of just generally thinking about health effect, sometimes I think of this as kind of like a alpha particle is like a cannon. It's super dangerous if you're close, but after you get outside of 50 yards, the cannon can't even touch you. Beta particle is more like shooting a rifle. It's dangerous. It has a lot longer range, but you could probably stop it with a brick wall. And then a gamma ray is like a radio wave. It's the most penetrating, but it does the least amount of damage. And so it's kind of that balance of both. So the way to think about it is alpha and beta are the most dangerous if you get them ingested inside your body, but they're the easiest to block and keep out of your body. You probably can't protect yourself from gamma rays in the sense, except to just avoid staying in their presence. Now, a lot of times we use radioactivity for good things. This is what we call a PET scan, or positron emission tomography. This is used to image tissue, and basically it's a positron emitting type material, and there's a lot of things that we could a lot of elements that you could put in your body that would be taken up naturally by the body, such as carbon, that can be found in a radioactive form that's actually a positron emitting. And the key is that when it's positron emitting, it will actually hit an electron in nearby, and it will actually, because it is the anti-electron, it will just disappear, and a gamma waves will take off in opposite directions from where that disappearance occurs. And that's a unique situation. There may be gamma rays flying around, but it's very seldom that they are emitting from the same point in opposite directions. And that's how we know that this is coming from that positron emitter. So these are two different positron scans or PET scans of someone's head region. And you can see on the left there's been a lot of activity going on in there that uptook the positron emitting material. And on the right, the activity is slowed down or settled down, so there's been less uptake of the positron emitting material. And this is used basically to really measure brain activity. It's common to do radiation therapy because cancer cells are gluttons and they will take on anything that's brought in, so you might purposely introduce something that's an alpha emitter or a beta emitter, and the cancer cells will, in their selfishness, take those in, and then they're very close proximity to an alpha beta emitter, so it will kill the cancer cells. It's possible to do a less dangerous type of radioactivity like a gamma emitter and destroy microbes. We found that if you irradiate food, it will often increase the shelf life. Here's a non-irradiated set of potatoes, and for comparison, here's an irradiated set of potatoes after the exact same time. And it can also kill microorganisms that might also cause rotting or spoilage, and obviously can kill small insects. The other application of just radioactivity, and remember once again, this is the very low energy form of the three nuclear reactions. It might be used just for power for spacecraft instruments and naval vessels. You'll probably remember the scene in The Martian where Matt Damon basically utilized radioactivity to keep his solar rover warm. Keep that clear in your head, though, that that's just radioactivity. It's on the same power level as just burning coal. That isn't necessarily like what would power a naval vessel as far as like running the props on the ship. That's one of the other nuclear reactions, such as fission. But because that is occurring on the ship already, there may be radioactive materials that you can just harvest the radioactivity and use it to do low power type items such as heating. Okay, so I hope that these videos have helped you understand how nuclear chemistry differs from non-nuclear chemistry. I want you to spend some time memorizing the 5 types of particles that are released. I want you to work on that graph and know the trends about where the line of stability is by dividing neutrons by protons. Know that if you're above the line of stability, it's probably going to be beta emission. If you're below the line of stability, positron emission or electron capture. And if you're well above protons of 83 or bismuth, it's probably alpha decay. And then I'd like for you to know kind of some of the health effects of the 3 common alpha, beta, and gamma particles in terms of penetrating power, and also the ionizability, which would be translated into danger. And then also know some of the common uses we make of radioactivity. And I hope that this video helps.